Okay, Assalamualaikum warahmatullahi wabarakatuh, and good morning to you all. So hopefully everybody is doing fine today. As I promised, we are going to do our quiz again this morning, which is quiz number 5. So I hope everybody you have downloaded the quiz from WhatsApp group. And make sure also that you fill in the attendance for today. So what I'm going to do now, I'm going to explain a bit about the quiz that you have to do. So I'm going to go to presentation mode now. Okay, so I hope everybody you can see what we have here on the screen. This is your quiz, okay? That is a two-dimensional frame structure. That's two-dimensional frame structure. Number one, as usual, you have to build the finite element model of this structure. Remember, this is a frame. Please take a note on the angle of the component, and we have two applied force. One is over here, and the other one is over here. Okay, so that is the first thing that you have to do. You need to build the finite element model of this structure. And once you have your model, you have your element numbering and node numbering, then you need to look at the element number 2, look at the element number 2 of your model, and then you have to state the orientation angle for that element. But of course, you need to answer this question number 2 by doing diagram or drawing. Remember that you have to decide on your local x-axis, and then after that, based on that, then you will have your orientation angle. And for the question number 3, you need to state the value, if you have the value anyway, of f to x, f to y, and m2, which is, of course, that relates to the node number 2. And again, which node number 2 is, that depends on your finite element model. And after that, you need to state the size of structural stiffness matrix K, before and after you introduce the boundary condition. So that's a very straightforward question. And of course, to answer the last question, which is question number 4, you need to understand that for every node, you have the degrees of freedom as stated here, dx, dy, and rotation for every node. Okay, so with that, then you can ask the question. Be careful, be careful. Please take a look at the global axis. Please take a look at the global axis. I put as the positive x global as going up. All right, positive x global as going up, because that will determine how you answer your question. So if you change the coordinate axis, of course you are wrong. All right, so with that, then you can start doing this. You have to submit the answer not later than 8:30. Okay, anything after 8:30, I'm not going to accept. I'm not going to give the mark. As usual, you are going to submit to that email. Okay, the email that you are normally submit your quiz. Okay, so with that, then you can begin to do your quiz now. Okay, so that is your quiz. Yeah, time is up now. So let's discuss our quiz. That quiz is, to my opinion, is very important. Uh, Probably among the most important among all the quizzes, because for a very simple reason that you have coordinate axis that is not what you normally see. Normally, x-axis is positive to the right and y-axis is going up. But in this case here, we are having different positive direction of x and y global axis. Sometimes we call global axis as reference axis. So you have to be very careful on that. And in reality, many of our structures, when you build the finite element model, the XYZ axis can be to any direction. So meaning that you have to be observant to that situation, and based on that, you will be able to accordingly decide what will be the orientation angle. And of course, when you want to decide orientation angle, number one, you have to decide where will be your x positive local axis. So now let's see how we solve this problem. Let me go to presentation. Okay, so hold on. I think I haven't. Where is the solution? Hold on. those are the list of the quiz that you have done. All right, so that is your question. And what you see over here is the finite element model. Okay, the finite element model. And the way you build your finite element model, that depends to you actually. And over here, that's the way I did it. You don't have to be having the same model as what we have here, because that depends the student actually. And the numbering is as what you have over there. By the way, I forgot to ask you, can you hear what I explained to you? You see what I have here on the screen?
Yes.
All right. And I forgot to do recording. Let me do recording first. How do that? All right, so that's your finite element model. By doing this, then that means you answer question number one. And as usual, we did it number one by the first thing to do is you have to decide on the locations of the node. So where you have the force, you have the node. That means you must have the node over here and the node over there. That's why you see this node number over here, node 2 and node 4, because you have the node over there. I think I should put a circle there to denote the node, but anyway, you know what I mean here. And when you have support, you will have the node. That means you have the node over here. That's node number one. When you are at the end of your structure, that's the node over here, node number 5. And when the structure, the component is changing direction, so that is the junction. So you will have the node over here. So that's why you have node over here, 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 and there. And the numbering is 1, 2, 3, 4, 4, 5. You have the element number 1, number 2, number 3, and number 4. Okay, so the next question here is we will decide the orientation angle of element number 2. That's the question, if not mistaken. So element number 2 is connecting node 2 and 3. That is element number 2, which we have over here. And it's up to you to which direction you will do your positive local axis. In my case, I do it based on what I regard as practical later on, from the low node number to higher node number. So that is my axis, local axis X. The direction is from node number 2 to node number 3. And because of that, then the way you measure the theta is as what you see over here. From positive X local, from positive X global to positive X local, and the direction is counterclockwise. So that's what you have over here. And you have to state the value, which in this case, the value is going to be 180, okay, plus when it is straight, when it is up to here is 180, and then you have to add 45 degree. All right, so it is going to be 180 plus 45, which is going to be 225 degree. And the next question is the external forces of node number 2, F2x, F2y, and M2. So that is the answer. So now you see here that this 1000 Newton, that arrow is along the x-axis. That arrow is along x-axis. Okay, that is the x direction, vertical, and this force is also vertical. So meaning now this 1000 Newton force is not along the y-axis, which normally you are accustomed to, but now it is vertical axis is x, and positive x is going up. So that's the reason why this 1000 Newton is negative. And y-axis F to y is 0 because y now is horizontal and you don't see the force. And in this case, positive y is horizontal to the left direction. And you don't see any applied moment here. You don't see any applied moment. So for that reason, then M2 moment external at node number 2 is 0, right? So that's question number 3, and that's the answer. And what about the size of your structural stiffness matrix? That depends on the number of nodes. You have 5 nodes, 1, 2, 3, 4, 5. And at each node, you got 3 degrees of freedom. That means you have 15, because 5 multiplied by 3 is 15. So it is going to be 15 by 15. But that's before the introduction of the boundary condition. And of course, in this case, node number 1 is fixed. Remember that we can have pin joint, you can have roller joint, but in this case, it is fixed. That means it cannot move in X, in Y, and it cannot rotate. So D1X, D1Y, and rotation 1, they are 0. Because of that, then you are going to reduce by 3 degrees of freedom. Then that's the reason that we have this answer over here. Before you introduce the boundary condition, it is 15 by 15. And after you introduce the boundary condition, it is 12 by 12. All right. So that is how I expect that you answer the quiz. If you don't answer according to the scheme, of course, you don't do that properly. Especially make sure that you answer question number 2 by showing this diagram. Then by doing this, I know that you understand. And also, if you answer question number 1, okay, the finite element model must involve all numbering, node and elements, must involve the forces that being applied there, this force and that force. And also you need to show as well the support, all right? And don't forget to show also the X and Y axis, global axis. By doing that, then you do a proper finite element model. This is our quiz number 5. I expect by now you understand, you know what you need to do with this kind of question. Okay, so with that, then yeah, that's your quiz. I hope I can do 2 more quiz. So after you have your mid-semester break, you're going to come back. I expect that I will do 2 more quiz. One is on vibration, and the other one hopefully on heat transfer. So at least I can do 2 more quiz. If I can do more, that's going to be better. By the way, the quiz 10%. all right, the quiz 10%, so that all the quiz that you have done or you will do the average, and then that's going to be the 10% of the quiz. All right. So yeah, that's your quiz. Is there any question? Any question regarding how to answer the quiz? When you come back from your mid-semester break, the plan from the college is that straight away you will do your test one. Okay, straight away you will do your test one, and test one will cover up to the frame. So you have to prepare yourself doing this, which also involve frame. So you have to make sure that you know how to do frame modeling. Okay, is there any question? All right, if there is no question, okay, then we will have a break. So not all of you answer the can submit on time. So anybody that cannot submit on time, then simply I just cannot accept, because your focus here is not to submit complete answer. The focus here is that you submit on time. Actually, that's the quiz. If you don't submit on time, then I cannot accept. Total time I gave you 15 minutes. All right. So anybody that couldn't submit on time, so I'm very sorry. I'm not going to accept for whatever excuse that you have, because you can finish this in 5 minutes and straight away you submit on time. Okay. All right. So with that, then we are going to have a break for 15 minutes or so. We are going to start again at 9:05. Okay, 5 minutes past 9. So we are going to start again at 9:05, and you can have your break now. All right. So see you at 9:05. Thank you. Okay, so we start again. So what we will do today is we are going to look again at frame, and the one example is going to be discussed here. So for that, I will go to presentation mode. Okay, so can you respond to me that you have this example? We have that frame with red color over there.
Yes, Prof.
So that is the problem. So when you do your test later on, what you are going to see first is the structure, not the finite element model. Okay, structure. So what you have there on the screen is a kind of a simple frame. Okay, kind of a portal gate, and the loads are given there. Okay, the loads are also given there. One load is over here, and the other load is over there. This load here is in the form of force, and this one here is, of course, that's a bending moment. All right. So those are the load, and this frame here is being fixed at the bottom here. So the left, I call it leg, the left leg is planted here, fixed support, and the right leg is also fixed. So with that, then you understand that this point couldn't move in horizontal, vertical, and cannot rotate. The same for this here. So those are the information that you have. And of course, you need to identify what is the material, what is the cross-sectional area. For each member, we have a vertical and horizontal here. And also make sure that you know the moment of inertia. Okay, so those are the data that you need to have. All right, so based on this, of course, then you are going to build your finite element model. So number one, you need to specify the node position. One is going to be over, sorry. So the node is going to be over here. I have to put, all right, one node over there. The reason is, of course, because you have the force. And of course, you will have another node at this location because you have the applied bending moment over here. You need nodes at support. So that means you will have one over here and also another one over there. Okay, so now let's check. Do we need more nodes? We have the loads and we have the nodes over there. We have the supports and we have the nodes as well. You are at the end of your structure, okay. These are covered. You have over here changing direction from vertical to horizontal, but you have the node already over there. All right, so that means we have all the nodes that we need. And of course, you put node numbering, like 1 over here, node number 2, number 3, and last, number 4. And don't forget the element number. So that's the way I will do. And this is element number 3. So with that, then we have a complete finite element model. In fact, that is how we arrive to this finite element model, right? Node 1, 2, 3, 4 over here, the same as what we have over here. And element number 1, element number 2, and element number 3. So, yeah, so that's the way you do it. You start with, you understand your structure, and based on your structural understanding, observation, your understanding on structure, then you build your finite element model. So this is our finite element model with all the dimension given, and the cross-sectional area is the same for element number 1, 2, and 3, and the moment of inertia is not the same. For element number 1 and 3, okay, for the vertical element, the moment of inertia 200. For the horizontal element, number 2, moment of inertia is 100. Okay, so please make sure that you are observant to that condition. All right, is there any question to our finite element model? Okay, no question, then let's carry on. So now what you need to do, you will have to build the equations. You have to calculate the structural equation, but of course, you need to first find out, you need to first calculate the element equation. You have 3 equations for the element equation. So that means you have to begin with element number 1, and then number 2, and finally element number 3. And the equation, you have learned that equation, which is as what we have over here. So that is the terms, that is the symbol that you have to be familiar with this element, so that you can calculate the equation. As usual, it is going to be F equal to KD, all right? F equal to KD. And of course, in this case here, the size of the element depends on degree of freedom. You have total 6 degrees of freedom. At node number 1, you have the x dy, the x dy rotation 1. At node number 2, you have the x dy and also rotation. And the force accordingly is going to be Fx, Fy, and moment at its node. Because of that, then we have 6 set of forces, which include the moment, of course, and 6 set of displacement that will include the rotation. And because of that, the size of K is going to be 6 by 6 as given here. And A is, of course, cross-section area. I, your moment of inertia. E is the material. And L is the length of the element. What about C and S? Those are cosinus and sinus. So meaning C square, meaning cosinus square. And of course, as what we have discussed before, theta is measured from positive x global to positive x local. And the reason why we can write F1, F1, M1, F2, F2, M2, so 1, 1, 1, 2, 2, 2, is because it is beginning with 1 followed by 2. The reason is because the positive x local is from 1 to 2. So that's the reason. You cannot do it in other way. You cannot do it in other way. If you don't do it in this way, in this the way we agree, then you are wrong. Then you are wrong. So be careful, because you might make mistake from the beginning. Okay, so with that here, then what you need to do, you need to apply this equation to the case that you have. So let's go to element number 1. That's element number 1. Number 1, you have to decide. The first thing is going to be what will be the positive x local axis. I decided from 1 to 2. So that's your theta. And cosinus, sinus, you get it. So based on that, then you can calculate all the ingredients like I over L, E over L, 12I over L squared, etc. You know your cosinus square, you know your sinus square based on this angle, then that will be the equation of element number 1. It is 6 by 6. All right. What about element number 2? That is our element number 2, horizontal. So that's the way I do my theta. I decided for practicality later on that the theta is going to be measured as before. But now, what about the X positive local? X positive local, I want it to be from low node to high node, from 2 to 3. Because of that, okay, then X local and X global, they are parallel. They are parallel. See here, they are parallel. Because of that, then the theta is 0. And of course, you calculate your sinus and cosinus. Based on that, you can calculate the ingredients, 12I over L. Be careful. I for the element number 2 is not the same as I for the element number 1. I for element number 2 is 100. Remember, element number 1, I is 200. See here, I is 200 over here. All right, so because of that, then we have our element equation for element number 2, which is given over here. You see, I write F2, F2, M2, F3, F3, M3. Why? Because it is from 2 to 3. Finally, our element equation number 3, which is that element. And now it is horizontal. It is vertical. We have node number 3 and node number 4. For element number 3, number 1 thing that I have to do, I need to decide local x-axis. So I decide the direction is from node 3 to node 4, from 3 to 4. That's the reason why x positive local is going down. Not going up, but it's going down. And theta is measured from x positive global to x positive local. And the value is as given there. And you get your sinus and sines. And you can calculate your element equation. Please observe that it is from 3 to 4. So that is the reason why we write 3, 3, 3, 4, 4, 4. If, let's say, you decide that x positive local is going up, all right? X positive local is going up because probably you like going up as positive, then the theta is going to be 90, okay? The theta is going to be 90, but you cannot write down as F3x, F3y, M3, F4x, F4y, M4. You cannot write like this. You cannot write like this because now it is from 4 to 3. Then you have to write your force and displacement as 4, 4, 4, 3, 3, 3. So that's different. That's the difference. All right. Okay. So with that here, then I finish all the element equation. What you need to do now is you need to construct the structural equation. If you can do it properly, okay, then your structural equation is going to be 12 by 12. Okay, it's going to be 12 by 12. So that means you need to expand your element equation from 6 by 6 into 12 by 12 because you got 4 nodes. So expand every equation, element equation, from 6 by 6 to 12 by 12, and then you combine them all together. All right, you combine them all together. So you are going to end up with a 12 by 12 structural equation. After that, you need to introduce the boundary condition, which is going to be at node 1, at node 4. At node number 1, it is fully fixed. That means d1x, d1y, rotation 1, they are 0. If you look at node number 4, fully fixed, so d4x, d4y, and rotation 4, those are 0. That means you are going to have 6 degrees of freedom to delete from 12 by 12. You deduct 6 degrees of freedom, then you will have at the end 6 by 6. So before boundary condition 12 by 12, after you introduce the boundary condition, it is going to be 6 by 6. So that equation is given over here. This is your structural equation after you introduce the boundary condition. And if you look at what we have here, now the forces we are looking at, those are only at node number 2 and at node number 3. Okay? Look, it is F2, M2, F3, M3. Only external forces, applied forces at node number 2 and 3. Anything to do with node number 1 and node number 4, we delete the reason is, of course, we have those as support and they cannot move. Then d1x, d1y, d rotation 1, d4x, y, and rotation 4, they're gone from the original equation, and we end up here with a structural equation which are 6 by 6 after you introduce the boundary condition. And now what we have here is all the forces that we know. The forces that we do not know, the reactions, they are not here. So F2x, 10,000, they are all 0 except F2x and M3. Please take a note that M3, 5,000, these are positive. The reason is because this 5,000 at node number 3, applied moment is positive because positive moment in this case is when it is counterclockwise. Remember, that is our agreement. That's the convention for positive moment direction. Counterclockwise is positive, clockwise is negative. What about the forces? The forces, the positive, is going to be when it is along the positive axis direction. And what you have here, x positive is to the right. Y positive is going up. So that means this 10,000 is going to be positive, and we call it F2X because it is at node number 2 and it is at along the x direction, and it is positive. The reason is because, of course, positive is to the right direction. So what you have here is going to be positive F2X and positive M3. And again, all the displacement here, these are variable. These are variable. So that is logical that what you want to find is all these variables, t twigs up to rotation 3. And if you can do it, then this is the result. Okay, so the unit is going to be based on the unit that you have, of course. In our case here, then the unit is because the problem is given in, if you look at what we have here, dimensions given inch, force given pound, and moment as what you have here is, of course, pound inch. So those are the unit that you have to consistently use, except for the rotation. The rotation here is always we do it in radian. So I'm going to write it here. The rotation is given in radian. Okay. So this this rotation here, for example, rotation at node number 2 is negative 0.00153. That is in radian, and it is negative. That means it is clockwise. Okay, meaning that it is clockwise. The rotation is clockwise. So that is the idea. So it is in radian. So you see, that's the unit for the rotation, and you know the direction from whether it is positive or negative. Now, once you have the displacements, okay, then of course you can calculate the reactions. You calculate reaction simply just by going to the structural equation, the complete structural equation, which involve the forces at the node, F1x, 2x, moment 1, F for x, F for y, moment 4, okay. And then, of course, we'll have already your all displacement. You can calculate the reaction, all right? You can calculate the reaction at node number 1 and at node number 4, as what you have done before for the truss and bar. And of course, after that, what you can do, you can calculate the internal forces for each element. For example, for the element number 1, then you can calculate forces at node number 1 and at node number 2, which you will find here. All right, which you find here. These are the displacement related to the element number 1. And these are the result, the internal forces. And of course, now remember, we are talking global coordinates. So the forces, these are all in global coordinate. The internal forces are in global coordinate. When you have this, then of course you can write down all these forces onto your element. This is element number 1. Okay, this is element number 1, and the forces are given over here, which is, of course, you get it from this result here. So you can write down this result onto your equation, onto your element diagram. And of course, in following the positive direction as given over here. So for example, M1 and M2, these are positive. That means they are counterclockwise. All right, so that is how we do it. And so, yeah, those are the example for frame. So later when you do your test number 1, okay, everything that you will do is going to be based on global coordinate, not on local coordinate, right? So your answer should be based on global coordinate, not local coordinate, except, of course, you need to find the local positive x-axis first, because you need to calculate the theta, the sinus and sinus theta. All right. So with that, then we finish this example of frame. Is there any question from you? All right. Is there any question?
Prof, can I ask something?
Sure. Yes, please go ahead.
May I ask, why only in the bar and the beam and frame we only have moment, and why not in bar and truss?
Okay. This question, to answer this question, we need to go back to statics and strength of material. Okay. So I hope you still remember your trust long time ago. When we talk about trust, okay, trust is a connection. Right? Trust is a collection of members of structural components. Okay, and if you notice, trust connection to another trust, so the connection between members, I'm going to stop sharing. So I hope you can see me now. I think so. Yeah. Look at this. I have this member and I have that member. All right. So now let's talk about trust. These two members, it looks like a bar. These are practically looks like a bar. And now you connect this to that, like that. Okay, so I hope you can see me. You can see this red bars, okay, red structure. Now, you begin to think, how am I going to connect this to that? There are many ways. There are two ways in general. Number one, you do welding, okay? You do welding. So, if you connect this component to that component by welding at the junction, okay, the behavior is not going to be the same if you connect this and that with pin joint. So you see here, we have difference of connection. You do either by welding, or another possibility is you do by pin joint. If you do by pin joint, then you have truss. Okay? If you do by pin joint, then you will have truss. If you do by welding, then you are going to have frame. So if it is truss structure, meaning that it is connected by pin joint, okay, then you need to have the support, for example, over here and over there, okay, also pin joint. So meaning this is going to be pin joint support, this is pin joint support, and the junction here is also going to be pin joint support. That is truss. And if you do it like that, if you go to static long time ago, probably in your diploma, probably, then you will notice that there is no bending moment at all. There is no moment at the joint. At the joint, at the support, there will be no moment. Okay? And if there is no moment, you will have only what? You will have only force in X and Y. So if you are in doubt, you can open again your book, Merriam or and Johnson, whatever book on statics, then you will find that, yeah, there is no moment. And that is trust. That is trust. And the trust itself, of course, at the joint, you will have X and Y direction because it is two-dimensional, Fx, Fy. But the resultant is always going to be along the axis. That is the takdir. That's the nature of trust. If it is pin joint, the resultant of Fx and Fy actually is axial. What does it mean? It means that trust is having similar behavior to bar. Why? Because bar only talk about having this kind of behavior, which is axial force, axial displacement. All right. In fact, we discussed before that thrust is actually bar, but in two-dimensional. So bar like this, if I hold it like that, and I apply the force like that, it is bar. It is bar. Definitely it is bar. Because you have only axial behavior. Okay? So if I add another component and I connect this to that, and the loading is along that way, it is bar. Everything is axial. But once you begin to have that connection is pin joint, then you have thrust. Because now the force is in X and Y, but resultant is still axial. Okay, so that's why if you look at the theory, you can go to the book or you can go to the slide that we got thrust element equation by transforming the bar, doing vector transformation. Okay, so by now then I hope you understand what thrust is. Now what about frame? If these two I connect by welding, all right, if these two I connect by welding over there, and the support is fixed, meaning that the support is clamped. That means if it is clamped, then of course it cannot do displacement horizontal, it cannot do displacement vertical, and it cannot rotate. If it cannot rotate, that means it will have moment reaction. Then of course we are talking frame. Right, we are talking frame. Because now we have also moment. And if it is welding, okay, at the junction, then of course, potentially you will have bending moment over there. So if you have moment, force in X, force in Y, then of course you are talking frame. Now, what about now if this is also welding? All right, so it is a frame. But what about now if the support is also not welding, but pin joint support? So over here at the junction, it is welding, but at the support, it is not welding, but pin joint. Are they truss or are they beam or frame? So it is not truss. Why it is not truss? Because if you have this as welding, then potentially you will have moment at any point. If you have moment at any point, then you do not talk truss. You are talking frame. All right. So I hope that answers your question. That is a long answer. And that is a good question because it is always going to be in the test, asking your understanding. What is the difference between this and that? What is the difference between this element to that element? What is the similarity between this element and that element? Yeah. Okay. Any other question? All right. Do you have any other question? Okay, so if you don't have any question, probably I will do another 5 minutes. Okay, so I'm going to remember that we skip one slide when we talk about bar. That is, we skip on the what we call as shape function. Okay, shape function. In your test, I'm going to ask you shape function. Not the theory of it, but how you are going to use shape function to find displacement. So now I'm going to go to presentation. All right. So I hope you can see what we have here on the screen. On your test, when we are talking about bar, of course, I'm going to test you on bar. I'm going to test you on frame, and I'm going to test you on thrust. So you are going to do a calculation. But of course, I'm not going to give you the finite element model. I'm going to give you the structure. So let's say you have this finite element model, okay? You have this finite element model. And the question is also involving this. I might ask you displacement at a point 20 inch from the right end. So the question here is displacement at a point 20 inch from the right end. So number one, you want to make sure that we talk the same language. Okay? Right end. What is right end over here? So this here is not right end. This is left end. So this is left. And that means this is right. This is right end. So make sure that we have the same understanding. Otherwise, you are going to be in trouble. All right. So this is left on the left. This is right on the right. 20 inch from the right end. That means we are talking this point somewhere over here. All right. Why? Because the length of this element number 3 is 50 inch. So this means that 20 inch from the right end, of course, that's the point. And please make sure that you identify that point belongs to which element. So if you look at what we have over here, that point belongs to element number 3. So if it is element number 3, okay, then you have to identify which node belong to element number 3, which is going to be this node and that node, node 3 and node number 4. Make sure you know the displacements at that node, node 3, and also at node number 4, D3x and D4x. This is bar, this is not thrust. So meaning you have only one degree of freedom, D3x and D4x. Once you know the displacement at node number 3 and 4, D3x and D4x, then you can calculate displacement at that point, right? You can calculate the displacement at that point. So let's say that this is this element, okay? That is element number 3, and node is 3 and 4. So that is going to be your x-axis, all right? And your x is measured from left. So you see that element, okay? Of course, you know, x positive to the right in this case, and this x here is measured from node number 3. So now you understand that at that point, x is 0. At that point, at node number 4, x is 50. And over here, all right, that point, of course, it is going to be 30. Why 30? Because total is 50. And this point here, that point, okay, actually is 20 inches from the right. That means from the left, x value is going to be 30. Okay, so remember, identify the point belong to which element. Identify the node number. Of course, when you do finite element analysis, you will find displacement at node 3 and at node 4. Of course, in this case, node 4, you know, before x is 0, right, actually, the displacement. But you still have to find displacement at node number 3. Once you get displacement at node 3 and also node 4, all right, then you are going to also identify this location here. What is the value of x? The value of x is going to be measured from the node at the beginning of that element, which is, of course, measured from node number 3. Node 3 is 50, sorry, 0, x 0, node 4, x is 50. Then, of course, you know that this point there actually will give you the x equal to 30. All right. What is the length of this element? L. The length of element L is, of course, 50. When you have established all those information, okay, then you can come back here. You can come back here to this element, okay, and you will use this equation. You will use this equation. What is this equation? This is displacement function or displacement equation. What is u? U is displacement in x direction. So that is x-axis. U is displacement along x-axis. At node number 1, displacement, of course, d1x. So at node number 2, u, of course, equal to d2x, displacement at node number 2. You have got your d1x and d2x. Finally, of course, in our example just now, we are talking d3x and d4x. And u, what we want to find out is along that point there. Okay, so of course, in this case, we are talking node 3 and node 4. All right, and of course, all the forces and all the displacement relates to node 3 and node 4. So in this case here, of course, it is going to be 3. Of course, it is going to be 3, and it is going to be 4. D3x, D4x. L in our case is going to be 50. X in our case is going to be 30. So because of that, then you can find your U, which is displacement of that point, which is going to be 1 minus 30 divided by L, you got the result, multiplied by D3x plus x over L, which is 30 over 50, multiplied by D4x. Then you are going to have U. So make sure you know how to answer such question, which is what will be the value of displacement at a point 20 inch from the right hand. So I can ask you different question, 20 inch from the left, or I can ask you also, what about displacement exactly at the middle? All right, you have to solve it according to the procedure that I explained to you just now. All right, so with that, I finish this example. By explaining this, then I have explained to you everything that you need to prepare for you to do your test one. Okay, is there any question? Suddenly students are less, so students are trickling away. We start with how many students when we did the quiz, and now we have only not so many students anymore. Okay. I finished everything. Okay. So please make sure that you learn, you study what we have been discussing so far up to this week. Okay. And on Wednesday, I will do ANSYS demonstration on how we can conduct finite element modeling and analysis using a frame combined with truss structure, because it is possible that you will have combination of element frame combined with truss, for example. So it is important that you know how to do finite element analysis on combination of frame and truss, later on frame with shell, okay, because in reality, of course, you will have combination of a different shape for your system. So that's what we'll do. But before that, I'm going to invite you if you have any question. Okay, so please make sure that Wednesday morning, you ask me questions on things that you do not understand. And then we are going to proceed with our ANSYS demonstration. Okay. All right. So with that, then I finished this course today, which is our, well, by next week you have your holiday and break semester, and the week after that you will have your, well, my understanding, that's going to be your test week. Okay. So with that, then I thank you so much for attending the course. And with that, then I finish this course. You can later on find the recording on the usual link, the same link. So with that, then thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and good morning to you all. Thank you very much.
Thank you, Prof.
Thank you, Prof.
Thank you, Prof.
Thank you, bro.